computer if somebody needs it later. Okay, so I'm going to go ahead and start with my introduction right here. There we go. This should be my introduction slides here. And so obviously this is Msec 7320 Nanocomposites, specifically focused on polymer nanocomposites, but I'll do some other stuff there. So in the syllabus, you may find that on Canvas. A lot of you have already got my invite there. For some reason, it didn't populate the graduate students into Canvas. So that's why I sent you those invites, and everybody but one person seems to have accepted the invite so that we can do that. Anyway, so for our grade, we'll have an in-class presentation, at least one. I'm pretty sure we're only going to have one, but I put the S there just in case we have a second one. I'm hoping to get a couple guest lecturers to come in and talk about their nanomaterials research. We're going to do a critical literature review. That's of some paper, of a literature paper of either my or your choosing. Preferably, it would be something closer to your research so that you can actually use it for a critical analysis of that. We'll go over what all those critical analyses are, and then it'll be a up to 4-page review of that work. And then the midterm is going to be have 2 components of it. So let me go ahead and go to the in-class presentations here. If you want me to select the topic, I can, and then I can give you the topic, and then you can have at least 5 references. With those 5 references, you must discuss the nanomaterial type. Preferably the 5 references all use the same nanomaterial type. And then maybe they have different uses, different processes, different analyses. And so you can compare and contrast those topics as far as the presentation goes. So basically you would be picking a type of nanomaterial and then looking at 5 different references to see how they handled that material. Or you can pick one yourself, but you still have to do the same thing. You still have to have 5 references, preferably of the same material type, and then look at the different processing that people use. Some people use solution processing, melt processing, et cetera. And we'll talk about the different process methods possible with our system as we go forward. Okay, any questions about that in-class presentation? Okay, so the next thing we have is the critical review. The critical review, I'll again assign this later in the semester, and I will review this right here. The critical review is going to have to give, you're going to have to talk about the introduction and background and give anything that they might not have included, some background that you know that they didn't mention. That would be a good thing to add here. The methods they use, specifically like their processing methods and any sample prep methods that they'd be using for that, because nanomaterials are a little different than regular processing and materials prep. And a lot of the analytical methods are very different from what we see as well. So it'll be interesting to look at the different methods that you guys come up with for your critical review. Then you want to look at their results and see if they came to generally the correct conclusion, or if they missed something that they might have seen in there, or you might have say, oh, well, but they could use it for this. That would be a nice thing to have there. And then in the discussion, does all of their results support their hypothesis or not? What other materials should they have used? What other analysis should they have used? Did they answer all of the underlying questions you had as you were reading through there? And then I would like you to also expand upon that and say, well, where could they do their future work? Could they do mechanical analysis or thermal analysis or some other analyses that would add something to their story? So that's what we're going to do with our critical literature review. Any questions on that? And I'll have closer due dates as we move closer, and I'll tell you those as we go. I'll give you at least a month before those are due. Okay, the next thing is the midterm. The midterm is going to have one in-class portion. It'll be a short in-class portion. It's basically going to be definitions, polymer types, techniques, uses, processes, and different little things like that. These are going to be short answers, answer the question kind of things, fill in the blank kind of stuff. I just want to make sure that you have, some of these things put to memory. And then the second half of it is going to be a take home. And the take home is going to be discuss 3 of the 5 topics that I've offered. And so, and I'll have instructions about that. So In this particular topic, we're going to look at what is the benefit of using a spherical versus a platy type polymer. What's the advantages of using a one-dimensional versus a three-dimensional nanoparticle? What's the advantage of using an elastomer? What property changes would happen if we used an elastomer versus a thermoset? So those are going to be some of the topics that we can discuss, that'll be discussed in those take-home exams. And then you'll have 24 hours to take them home and upload the answers to Canvas. So that will be something to have. The final exam will also be a take-home. It'll be probably the week before finals are offered to get you out of the, often running. And it'll be the same thing. I'll offer 8 topics, and you have to discuss 5 of them. Compare and contrast the filler, compare and contrast this analytical technique, do this example paragraph discusses is what's missing. What could they have used? What could they have done better? Those kind of things will be winding up on the take-home portions of the exams. Any questions on that? Okay. So a little bit about me, so am I just some, crazy lecturer who's never seen nanocomposites before? Well, let me tell you a little about me. I actually got my bachelor's of science and master's of science here at Texas State, back when it was Southwest Texas State University. I did all my work on small molecule synthesis and polymer synthesis. And so literally I've been working on polymer synthesis since 1988, including, my dissertation was on fluorinated polyamide amides for high temperature polymer work. And that also allowed me to do a summer internship in Japan. I spent 3 months in Japan working for a Japanese chemical company as part of my bachelor's degree. And so that was very interesting. And I can tell you stories about that as well. From there, I went to University of Florida for my PhD, did most of my work on heterocyclic polymer synthesis. Most of that was synthesis and or polymer synthesis, but I also was able to do a lot of computational chemistry because I ended up doing an internship at the Air Force at Wright-Patterson Air Force Base, using their supercomputer to calculate out atomic AM1, Austin Model 1, and some other semi-empirical models to look at electronic properties. And so that was really interesting as well. And so that all got rolled into my dissertation and included approximately 12 different crystal structures of materials as well. So that was it's pretty long and detailed dissertation. It was 186 pages. So I got a postdoc at the Sandia National Labs, which is a nuclear weapons lab. Learned a lot about that, did a lot of work on, again, polymer chemistry and different little aspects related to that, including I got my first patent while I was there. Then I moved over to the Naval Air Warfare Center, which is a Navy base that works on anything that falls off a plane and is supposed to. So I consider that one of those valuable learning experiences. I also ended up becoming an explosives team member. And so you'll actually see some of my nanomaterials work is actually explosives related or pyrotechnics related. And so did a lot of different projects there, was team lead and team member. And I also got trained as a Lean Six Sigma black belt through the Navy, and extensive project management training. And that led me to my next position here in Texas, which was the senior chemist, and I eventually became the director of research for an SBIR company up in Austin. I wrote over 30 SBIRs, won 10 of them. So if you do the math, that's about 33% win ratio. So that's better than the national average. So we did pretty well there, including phase 1s and phase 2s. The most notable of them was the 3D printed food for space, which was a NASA project, which would have gone on, except some senator got a thing that we were wasting money by sending pizza to space. And so it got canned by a political reason, but it was really cool process. Then from there, I went on to become a principal polymer scientist for a company that made polymer aerogels. We actually made polyamide aerogels. They're commercializing it. In fact, the company is still going. They moved out to Massachusetts to get their, I helped design their pilot plant It's capable of producing 1 million square feet of polyimide aerogel film. And they're doing great right now, even with COVID. They're, exceeding their sales goals for that. So once they moved off there, I came back to Texas State, and I've actually been teaching at Texas State since about 2008, on and off, for different really things. For a couple of years, for 6 years, I taught Gen Chem, organic chemistry, and introduction to organic chemistry and spectroscopy. And then when I came back full-time as lecturer in 2019, I do general chemistry, organic chemistry, and polymer chemistry, and now nanocomposites. So if you look at my resume, about 16 publications, 5 book chapters, 39 proceedings, and 33 patents, including a European patent. So I've done a lot in both government labs, academic labs, and industrial labs. So I have like the experience of almost everywhere you can work as a chemist, except for maybe in the biological field or medical field. So you can ask me questions about that if you have questions. Okay. So any questions about that? All right. So here's some projects. This is a little small, but I've done polyimide aerogels, and the pore size of those aerogels is about 50 nanometers. And so we were looking at that. My first project with nanocomposites was actually surface enhanced Raman spectroscopy, where we took gold nanoparticles and coated them with conducting polymers to get an enhanced surface Raman detection for explosives. And that worked really well. We did some melt extrudable nanocomposites from liquid crystalline polymers. The interesting thing about that is that's using montmorillonite clay, but it's incompatible with liquid crystals. So we actually had to make liquid crystal surfactants that would compatibilize them with the liquid crystal, and it made for oxygen and water barriers. So if you can imagine, for food packaging and that kind of thing. So that worked really well. We also did work on making nanocomposite ballistic transparent coatings. So for ballistics windows that aren't made out of glass, they're very prone to scratching. And so this coating was actually to help with the ballistics and help with the scratch coating, using an alternating polymer inorganic nanocomposite system that would give these transparent films on a molecular level, and it's a layer by layer assembly of that. We've also done some stuff with rocket propellant modifiers, mostly in the nanoparticles, both aluminum, magnesium, and silicon as nanoparticles for rocket propellant additives. It increases the rate of combustion of just standard hydrocarbon rocket propellants by up to 22%. So imagine you can get a little more thrust with the same amount of mass in your system. We've also done some conductive and transparent graphene coatings that do not involve surfactants, which is a little difficult. That's more of that's a very interesting project. Passive and thermally responsive polymer nanocomposites, meaning it's an electrically insulative but thermally conductive responsive polymer system. Did another one of my nanotin nanocomposite carbons for lithium ion cells. Nanosilicon for scintillators. Did a lot of work with nanosilicon, especially for the Army and the Navy. Everything from nanothermites to nano explosives to nano additives to nano fuels. So the next few projects are all about that. One of my special topics will actually be on, I was going to do nano energetics. And so I'll give you a whole rundown on energetics and nano energetics, and as things get smaller, how they are affected by their burn rates, and therefore can give you some other interesting ideas about how to use them in that kind of application. And then the last one, I also used elastomeric nanocomposites to decrease water transmission through submarine fly-through covers. So imagine you have these covers on top of the nuclear warheads inside nuclear submarines. They have these plastic covers, but water kept dripping through them, and so transpiring through them. So we made a nanocomposite material that decreased the water transmission by 99%, and it was still elastomeric enough to use as a fly-through cover. So those are some those are some different projects I've had related to nanocomposites. So I've been doing this for quite some time. So, but I don't know everything. I'm learning some stuff now, and I'm hoping to teach you a lot of the stuff I already know, and hoping to learn some stuff from you on your presentations. Okay. Any questions about that? Okay, so that's my introduction about me. And then what I'd like to do is also start with a review of just polymers itself, because a lot of what we're going to do is polymer nanocomposites. And so I kind of want to go a quick review of polymers themselves. If you have taken a polymer class, I'm sorry, I'm going to have to review this. If you haven't taken your polymer class, go ahead and I'm going to upload these slides. You can download these slides from Canvas and review them. And these definitions of polymers and different types of polymers and processing will be part of the midterm. So that's one place where you'll be able to go for studying for that for the midterm as well. Okay. So I'm going to go ahead and share my screen for polymers. Okay, so this should be my polymer one here. So the first thing I want to do is I want to say that I've been working on polymers since 1988. I've done a lot of different systems, everything from elastomers to aerogels to explosives, but I still don't know everything. I'm still learning stuff, and so there's always an opportunity to learn more. But the basics right here, these fundamentals will get you started on being able to find the different aspects you want to use and maybe translate it into something you might want to use in your own research in the future. Okay. So first thing is that, by definition, a polymer is a unit, many different units. Okay, so the poly means many, mer means unit or part, and so that by doing that, we just have large molecules. Now, if we look to nature, that's things like starches and proteins and chitin and all these different natural ones. But in most of polymer chemistry, the synthetic polymer chemistry is much simpler. Typically, we don't have 14 different types, or we don't have 1,000 different ways to arrange the 5 different things that are in our repeat units. So we tend to think of the synthetic polymers as simpler and less complex than the biological systems. So, but that doesn't mean they don't have different ways in which they can hook together. Most polymers are what we consider linear polymers, where they just grow from head to tail, all the way along. However, there are many different systems like polyethylene, or you can incorporate a trifunctional material, which will allow you to have a branched polymer. And branched polymers have different properties than linear polymers. The more linear the polymer is, it might have different properties like stronger or higher crystallinity. Branched polymers tend to be rubberier and have less crystallinity. But then you can have these perfectly designed branched polymers where you have 4 different things growing off from the same spark. That's a star-shaped polymer. If you just have the same length branch coming off at regular period along your main chain, that's considered a comb polymer. And some of the more robust thermally stable polymers from the 1950s and 60s were what we called ladder polymers, where you actually have 2 different polymer chains that are linked together all the way down. They tend to be very rigid, very tough, very poorly soluble, but because of that structure, they are very durable and highly useful for high temperature applications and places where you need something that has a great deal of rigidity and or strength. Excuse me. Okay. And then there's some that are semi-ladder, meaning they're still soluble, but they have that kind of linking 2 different polymer chains together. Then we can have network structures. In network structures, we tend to think about those as thermal sets. You have multiple places where you have these polymer chains intersecting and fusing together. And in those multiple sections, they no longer dissolve, they no longer have additional reactivity. They just fix into that position and are no longer processable. Denomers are slightly different, where you can have branches and branches and branches, usually in a very fixed periodicity where you have 3 branches, then 3 branches, then 3 branches, or 5 branches and 5 branches and 5 branches. And they can tend to be soluble and or used as surfactants, and many of them are used as drug delivery devices. You can infuse the inside of the dendrimer with a pharmaceutical, and then as it sits in a biological system, it can slowly diffuse out of that dendrimer system. So the dendrimer is different from the branched and the star shape by having a more regular structure. And so if you can imagine, it goes out and out and out until you actually have, you can have a complete solid surface on the outside where the inside is still disordered in polymer. Another opportunity there is to have rings around polymers like polyrotaxanes, or even having rings of rings of rings. And these have slightly different properties and have some interesting possibilities in molecular kind of interaction systems. Okay, and I'm going to talk about molecular interactions later, because molecular interactions between polymers is one thing, but molecular interaction between the polymer and the nanocomposite and the nanomaterial is another thing that really drives how easy it is to make the nanocomposite and what kind of properties you'll get from that nanocomposite. So we'll talk about that in additional slides. Okay, let's do that. Come on. Okay, so we have 2 basic classes of processing of polymers, not how you make them, but how you process them. So in the case of processing the materials, excuse me, I'm not used to talking this long. Okay. We can have what we call thermosets, and then we can have something that's called a thermoplastic. In the context of thermoset, that means you take your monomers and or polymers, you process them, and then they fix in that position, and they will not dissolve, they will not be reprocessed, they will not melt, they do not have elasticity after that. So the idea here is that it's set it and forget it. You're just done. And the only way to reuse it is to grind it up into a powder and just put it on the side. So these polymers don't melt or float after they are molded. So you can mold them in the process when it's the small molecules, but once it sets, they can no longer be processed. They're almost always cross-linked or kind of have a lattice type structure. Think epoxy systems where you have multiple ways in which they will not dissolve. They do, however, some of them do, they don't dissolve, but they will soak up a solvent and soften a little bit, but that's not the same. It does not dissolve and it cannot be reprocessed. In manufacturing, you must cross-link it in the shape you want. Okay, so you basically put it in your mold, heat it, and then it's done. One example of this is reaction injection molding, which is a cross-linked polyurethane system. They put it all in there, and once it sets, it's done. There's no dissolving or reprocessing or rework after that. Okay. And then a couple different examples that is polybutadiene. If you have cross-linking systems, polybutadiene itself can be soluble, but if you cross-link it with like sulfur, it becomes rubber. Epoxies, styrene butadiene can also be cross-linked. And then phenol formaldehyde. Phenol formaldehyde tends to form 2 to 3 different functional processes, and therefore it becomes that cross-linked thermoset. Okay. In contrast, thermoplastics are actually reusable because they melt and flow, and then they can be molded and remolded. And the point there is that they will flow when they are heated, and then once they're cooled down to their use temperature or room temperature, they no longer flow. So they seem to have a solid form. Even though they're not cross-linked and they're not fixed in that state, the intermolecular forces are holding them in position at that use temperature such that they don't flow or melt. Now, most of these can be dissolved in some kind of solvent because it's still individual polymers, and all you have to do is break up the intramolecular interactions between the polymers to get them to dissolve. And so when we look at manufacturing, these are actually easy to use because you could do injection molding, not reaction injection molding, actually just melting the polymer and injecting it into a mold, cooling it down enough so it holds its shape. Okay, and then if you don't like it, you can regrind it, and put it back through again. So typical examples of this are things like polyethylene, both high density and low density polyethylene, PVC, especially if it's plasticized. Polystyrene can be used in a number of different methods from the cups to the foams. Polyesters like polyethylene terephthalate, which we'll talk about independently, and polyamides, specifically nylons, like nylon 6 and nylon 6,6. Okay, so, oops. So now let's talk about different ways of classifying polymers by how we're going to use them. Okay, so the idea here is that if you want to have something that is going to be molded and then remolded and molded, then you want something what we call a plastic or a resin, where it typically can be amorphous to in the system or have a low level of crystallinity. They tend to be high molecular weight polymers such that they have a certain number of properties. And then they can, most often they are considered thermoplastics, but they can be used as thermosets. And these are commodity polymers. You can buy, you know, a rail car full of these pellets that they can be used again and again. And they're typically very low cost, very high volume, and you can use them for a bunch of different shaped and molded devices. In contrast, when we talk about fibers, those have to be processed in a way in such that they are, number one, have a high aspect ratio of thickness to length, and most fibers have very high crystallinity, meaning that when they're processed, they are drawn out, and as they're drawn out, they increase their crystallinity, and that increase in crystallinity gives them their high strength and high modulus. Okay, and so they tend to have decent elongation along that long axis, not along the short axis, but along the long axis. And that has to be a polymer that can be spun, meaning it either is milk processable such that it can be drawn out into these solid fibers, or solution processable so that it can be drawn out into these long fibers. Okay, so if we want to look at synthetic polymers, things like polyethylene terephthalate is actually used extensively in carpets. So the fibers in those carpets are polyethylene terephthalate. Then there's lots of acrylics and nylons. And if you think about polyester, it's polyethylene terephthalate and others that are used in fabrics that can be used in different types of fabrics, coatings, tents, etc. Anything where you can use a fiber. Now, in addition to that, some of the fibers that can be spun with solvents, such as Kevlar and Nomex, those are actually spun for a high crystallinity as well. And then they have to be used in a non-woven or non-twisted kind of aspect ratio, where we can actually see those fibers use their strength, their modulus, and their high strength, their tensile strength for their applications. Now, the next we have is elastomers. Now, unlike plastics, which will deform normally with heat, fibers which don't deform except for in their long elongation, elastomers will actually deform and then come back to that shape. Okay, so elastomers have either a intramolecular interaction between polymers, or it actually has a physical cross-link that allows the polymer to be extended and then come back to that original shape. So that extend and come back rapidly is normally done with either a cross-link or a chemical interaction between those. And so most of the time when we have rubbers, we set them, they can be set like natural rubber. Natural rubber has a cross-link added to it, usually with sulfur or some other compound there. And they're cross-linked and they cannot be reprocessed. So that elastomer in a natural rubber is a thermoset. It's formed and then it's done. However, there are thermoplastic elastomers. Think about these tend to be things like polyurethanes, where you can actually have polyurethane pellets that are elastic, and you can melt them and form them into films, and then actually they still have their elasticity. And that's because of the intramolecular interactions that allowed them to spring back from that. Excuse me. So there's two different processes there. They can either be cross-linked or have intermolecular forces. But the key thing is that they can come back once they're deformed. So then another way we can use them is as an adhesive. And we have several different kinds of adhesives we can use. And that functions either as a mechanical. In mechanical, we think of something like an epoxy, which it actually has fits inside any surface irregularities and forms this hard mechanical feature. Or we can have chemical adhesion. So in the case of chemical adhesion, you could have silicone on glass. Glass is almost perfectly flat. And so we actually have the silicone is chemically bonding reversibly to the surface of the glass and allows you to have that. So what this means is that your common types of adhesives can be things that either form that mechanical bond, things like cyanoacrylate, superglue, phenol, formaldehyde resins, epoxies. Those all form mostly mechanical type fasteners. But now if we look at things like silicones and pressure sensitive adhesives tend to form a chemical adhesion because they'll stick on there, chemically adhere, and then you can peel them off by breaking that chemical adhesion bond. Okay, and then the last one we can do is coatings. So in the case of plastics, think of the entire thing being the polymer. In fibers, thinking that individual fibers are bundles of the plastic. Elastomers, we have the entire bulk of it is typically the elastomer, although they can have fillers. The adhesive is where you have the part in between the two things you're trying to adhere. Now, coatings is just on one surface or possibly two surfaces of the other system. And these typically are done with either solutions or emulsions. In the case of emulsions, you would have small particles of your liquidized polymer in a surfactant. And then once it gets onto the surface, it breaks that surfactant, breaking that micelle up, and it flows across the surface. And then it dries, giving you your coating. Okay. And so if you think about polymer solutions, you can just spray them on, you can dip coat them, you can do a bunch of different ways to get that coating on there. For example, the nanomaterials project that I used with layer by layer, we actually used polymer solutions to make that system. When we look at emulsions, think about paint. Paint is an emulsion of solids and liquids, and when you shear it onto the surface, it breaks up those surfactants and they spread out and get dry. So a lot of the different things you have are the polyvinyl acetates. If you think about acrylic modified polymer, acrylic modified paints, that's where you're looking at. Styrene butadiene is a great solution processable material. Polyesters are typically a solution processed as well, but can be done in an emulsion as well. You can also have different types of polyurethanes work great in emulsions or in solution and work great as coatings for those systems as well. Okay, questions on classification by type, by application. Okay, so one of the big things with polymers is molecular weight. Okay, because when you have a small molecule, let's say you have ethylene, right? It's 2 carbons, 4 hydrogens, and it's a gas, right? Okay, so then we extend that up to 3 units of that. So that would make it hexane. Well, now it's not a gas anymore, it's a liquid. Okay, so now let's double that or triple that to give us a C18. That becomes a wax. It starts being a solid, but it's semi-amorphous, semi-crystalline, and it can be pushed around. Now let's extend that to 1 million molecular weight. Okay, polyethylene has, hundreds of thousands of molecular weight, and now it's a hard, tough, processable material. Okay, so in most of these polymer systems, you start with the properties of your monomer, and then whatever property you have, as the molecular weight increases, that property will improve. Boiling point, toughness, melting point, whatever, it is going to improve until it gets to a certain molecular weight, and then the benefits taper off. Okay, so anything above that taper off is what we call a high molecular weight polymer, because it has all of the properties that the polymer has, but it doesn't matter where the molecular weight is above that break point. Everything below that, where that break point is, where the properties are still changing with repeat units added, we would consider those oligomers or low molecular weight. Okay, so if we look at this last one here, polyethylene, if it's low molecular weight, about molecular weight of around 4,000, which is about 143 repeat units, it actually is a waxy solid and it melts around 92 degrees C. However, if we take that same thing and extend it up higher, so get over 200,000 units, so it's around a 6 million molecular weight, it's actually a nice, tough plastic that doesn't melt. You can melt process it around 136 degrees C, 138 degrees C. So going from a gas all the way through the waxy solids, all the way up to a nice, tough polymer is all based on the molecular weight, or what we call the degree of polymerization. So in the case of degree of polymerization, that's the number, the average number of repeat units of the monomer you have in that polymer. So it's sometimes called dP, it's sometimes called X sub N, it's sometimes just the N on the structure here. Okay, so that molecular weight, that degree of polymerization changes their properties. And so you'll actually see in some of the papers, we'll see they'll use a molecular weight or a degree of polymerization of 25 on one polymer system, and they'll use a degree of polymerization of 100, and they had to change their processing because the property of the polymer changed, or the properties changed, and the lower molecular weight polymer became more brittle, and the higher molecular weight polymer became more tough. So those are all different things that are affected by the molecular weight of these polymers. All right, questions on that? Okay, so in most cases, we really don't care what the in groups are. It's hard to find them sometimes. Sometimes you can find them by NMR. Sometimes you can find them by an analytical technique. For example, polyethylene glycols that have OHs on the ends are typically analyzed by free hydroxyl. So they actually do an acid-base titration to figure out how many alcohols are on there. And it'll give you a weight number average of alcohols per repeat unit, per polymer unit. And so they're kind of hard to find sometimes. Most of the time, they are ended up being hydrogen or whatever functional group you made that polymer out of. Let's say you have a polyamide, it's going to either be a carboxylic acid or an amine at the end of the system. So you'll see that kind of different thing. But once we get above a certain molecular weight, it's very difficult to find, and it really doesn't change. However, we can name them. For example, if we want two ends of the polymer to be reactive, for example, in the case of this one down here, the hydroxy polyethylene oxide here, we actually might want to use that to react with the polyurethane. So we need to know that there's an OH group at both ends. And so we can say that at one end, the alpha, which would be the head of this, has a hydrogen. And the reason we call that a hydrogen instead of a hydroxy is because the repeat unit is the oxyethylene. So it's the oxygen is included in the repeat unit. So that's why this is a hydro, even though it's an alcohol as the functionality, and omega hydroxy. So that tells you can actually use that as a big monomer to make an additional, much larger polymer in the system. Okay, so, but most of the time we don't care about that, but these are used extensively in particle modifications and in looking at nanoparticle incorporations, trying to coat them such that they're less or more reactive. So we'll see this kind of polyethylene oxides with two hydroxides on them in several different processing steps, what we'll see. All right, so another thing we can do is we can do what we call end capping. So end capping is more important when the end group is still functional. So let's say you have something like a polyamide, right? And so one of the end groups can be a carboxylic acid, or one of the end groups can be an amine. Well, amines will react with different things than carboxylic acids will. So sometimes you want to end cap those so they don't react further. Okay. But you can also add a monofunctional unit, and that will limit the molecular weight. Okay. So if, let's say, you're making a polymer and it has a diamine and a dicarboxylic acid, if you had perfect stoichiometry, this would create 1,000,000 molecular weight because each of the functional groups would react and react and react. But let's say you wanted to not have 1,000,000 molecular weight. So you put a monofunctional material in there, a monoamine, and then for every unit of monoamine you put in there, it's going to decrease the molecular weight to maybe have a more soluble process, a lower melt temperature. There's a bunch of different ways to do that. The other way to do that is you can actually compare block copolymers. So you'll grow a polymer to a certain length, and then you'll change the monomer and end cap it with other things. And that can be growing from both ends or just one end. So you can get a block copolymer 2 sections or a block copolymer 3 sections. This is used a lot in surfactants. So they have non-ionic surfactants that use these block copolymers. Another thing that they can do is you can actually tag them with something that you can see. One example is I actually had some polyimides that we were trying to limit their molecular weight. So we tagged it with a fluorine-containing monofunctional unit. And when we did the analysis by thermal analysis, we could see how much fluorine was incorporated. And by seeing how much fluorine was incorporated, we knew the exact molecular weight of each of the polymers. So those are different reasons to change that in group to do that. But most of the time, you can analyze these. If they're small enough, you can analyze them by NMR, something that is big and not in the same functional area as whatever you have. Sometimes you can do the hydroxyls, the carboxylic acids, or the amines by titration. Sometimes you can radio label them either with oxygen or carbon to see what you have. Or if you have a group that can be fluorescent, fluorescence is actually very sensitive. You can actually put an azo group or some kind of fluorescent dye hooked to the end, and you can do that. Or as the last one is, you add a halogen in group that you can detect by elemental analysis, which is the way I used to do it. So the end capping serves 3 purposes. It gives you an idea about molecular weight. It gives you an idea about what's at the end, can I use it? And it gives you an idea of how stable it is. For example, if you take THF, tetrahydrofuran, you can polymerize that to make poly-THF. However, it spontaneously converts back to liquid THF unless you end cap it. If you end cap it with T-butyl groups, it stays as poly-THF. So that's one of those weird things where end capping actually keeps it from going back to the monomer because of thermodynamics. Okay, so Carruthers is what we consider the godfather of polymer chemistry. He basically started the work with figuring out how polymers work, why they're different than other molecules, why they're different. And so back in the 30s, he decided that there was only 2 kinds of polymers. Don't worry, there's more. But he decided there's 2 kinds of polymers. There's what they called condensation polymers, which is polymers that would join together but then lose some small molecule. Water, acid, alcohol, something would lose a small molecule. And so something would condense out of the polymerization. And so you would lose mass, okay? So in all condensation polymers, you tend to lose mass, okay? And then he said there were the addition polymers. In addition polymers, you do not lose mass, okay? So in addition polymers, you start with a double bond typically, and you end up with all single bonds. And so that way you have, if you're doing an industrial process, you put in 100 pounds of styrene, you get 100 pounds of polystyrene out. So in an industrial process, addition polymers are highly favored because of that. Okay, there's one polymer that kind of fits both categories, which is polyurethanes, and I'll talk about that separately. Okay. So polyurethanes is this one. This is the one that doesn't fit either definition, because technically it describes a condensation polymer because it has two different functional groups. But when they react, they do not lose a molecule. So imagine all of your condensation polymers tend to have a functional group that converts to another functional group. In the case here, we have a carboxylic acid chloride reacting with an amine to generate acid. Most of the condensation polymers are some kind of carboxylic acid derivative, and we'll see that. But in the case of the polyurethanes, it doesn't follow that. It has two different functional groups. In theory, it should be a condensation polymer, but it doesn't lose a small molecule. So in theory, it should be an addition polymer, but it doesn't follow the mechanism of an addition polymer. So that's the one that kind of sticks out from the system that doesn't always work. So that's why the classification really didn't work very well in Carruthers' system. So a few years later, Flory, who came up with a lot of polymer processing parameters and different solvent systems and theories about this, came up with a different way of looking at it. And the different way of looking at it is to look at it as a stepped growth polymer. So a stepped growth polymer is one that will have grow by discrete units. So you have a carboxylic acid and an amine that works together, and that's one step. And then you have an amine on this side and a carboxylic acid, and one of those will react, then the other will react. So they're discrete steps of forming a bond, forming a bond, forming a bond. And they tend to grow in first getting monomers, dimers, trimers, tetramers. And so the molecular weight is small until the very end of the reaction. At the end of the reaction, you tend to have the high molecular weight system. In contrast, chain growth polymers are similar to those addition polymers, where you start growing on one of the monomers will start, and all the other polymers will react with that one that's growing, because it'll have a reactive end group that'll continue to grow. And that's called the chain growth polymer system. So in chain growth polymer system, your molecular weight increases immediately upon growing your chain. Step growth, your molecular weight slowly increases till the end. Chain growth, your molecular weight's increasing from the beginning. And so you can think of that the chains are all propagating from a single, from very few number of molecules, and they're all growing off those number of molecules. So that's a better definition by there, because in the case of the step growth polymer, we can actually classify polyurethane as a step growth polymer, even though it doesn't lose a molecule, because it discretely reacts the isocyanate with the amine or the alcohol to generate the next system. And all the chain growth polymers tend to be those same addition polymers we saw, like styrene and polybutadiene. Okay. All right. So then some important features of these step growth fermentations is that in the beginning, you have your monomers, and they immediately react to form dimers, and then trimers and tetramers and oligomers, and then they keep growing. And then right at the end of the reaction is when it tends to have its highest molecular weight. But notice, most of the time, the ends of the polymer are still reactive. You still have an amine or a carboxylic acid or something at the end of it there. And therefore, there's no need for a termination step. You can just add more monomer and get more polymerization to go. Okay. And the reaction mechanism does not change at any time during the polymerization. Okay. So most of the time, it's like an acid-base reaction or a nucleophile electrophile reaction that's just reacting to create a new functional group, and then they just keep going and going and going. In contrast, growth is different. Monomer is consumed very slowly, because only the chains are growing right here, but the molecular weight increases rapidly because you have all this monomer floating around, and then this chain is continuously growing while all this monomer is floating around it. And it continues to grow and continues to grow. And they typically grow by repeated addition on that growing chain that gives you that reactive site. Now, if you don't stop that, you can actually have the reactive site at the end of the polymer still be there. And those are called living polymer systems. where you can actually continuously add different monomers to that, and they will continue to grow. And the mechanism is starts with initiation. You have to create something that'll start growing those polymers, doing that addition reaction. Then there's the propagation step, which is whenever you react a monomer with it, it generates another reactive species, typically a radical, an anion, or a cation. And then it'll continue to grow until there's no more monomer. And then in most cases, you also find what we call a termination step, which is where you get rid of the reactive species at the end. You get rid of the anion, the cation, or the radical, and the polymer stops growing and it cannot grow again. Okay. So the mechanism changes. You initiate by starting a monomer with a reactive species. All the monomers continue to grow off that reactive species. And at the end, you terminate with either water, air, or something like that. Okay. Questions about step growth versus chain growth polymerizations? All right. So to compare and contrast, step growth usually reacts with the monomers, then oligomers, and typically step growth involves two different functional groups: an amine, a carboxylic acid, an alcohol, an acid chloride, or an ester and an acid chloride, something like that. There's two different functional groups that react to form a new functional group that is in the main chain of the polymer. In the growth system, it basically starts at one monomer unit, and it's in a sea of monomer units, and the polymers are just growing, and they're all growing at the same rate. So the molecular weight's increasing, but you still have this sea of monomer around it until it runs out of monomer to react. The polydispersity, the degree of polymerization tends to be low to moderate. We can get 1 million molecular weight, but any defect in any reactive group there creates an end to that polymer growing chain. So that's why our degree of polymerization tends to be low to moderate in our step growth material. And so you have to have both monomers very, very, very pure. Okay. In the case of chain growth, the degree of polymerization can be very high, millions of molecular weight. And the reason is you can have impure monomers as long as they don't react in a radical or an anion or cation formation. As long as they don't react in the growth mechanism, that doesn't matter. They do not affect the degree of polymerization. That's why chain growth polymers can be millions of molecular weight, while step growth polymers, it's difficult to get into the millions of molecular weight. In the case of step growth, monomers are consumed rapidly because monomers are immediately converted to dimers, trimers, tetramers. And again, the properties don't change until you have hundreds of repeat units together or thousands of repeat units. So the monomer is consumed the monomer is consumed very slowly. You can almost use the monomer as the solvent in chain growth. And at the end, you actually have this molten polymer. Molecular weight increases slowly because it's going stepwise. Molecular weight increases rapidly in chain growth because the individual chains are growing in a sea of monomer. No initiator is required. Sometimes they can help start, they'll help activate the reaction, but they're not required. And they use the same mechanism all the way through. In the case of chain growth, usually involves an initiator, and heat is enough of an initiator for several of these reactions. And then it has a propagation step, and then usually a termination step. There's no termination step required, or in a step growth, you can just keep adding those end groups, adding to those end groups. And typically in the chain growth, you do stop it so it doesn't react. The polymerization rate decreases as the functional groups are consumed. Think about that. As you're consuming those functional groups, you're in a solvent. The distance between the now monofunctional or difunctional groups, between those and the growing ends, are starting to get further and further apart. So that means that they have to diffuse further and further together to get to that. So that means the polymerization rate decreases all the way through the growth of those step growth polymers. However, in the case of the other one, the polymer increases initially until all of the monomer is consumed, because you're growing this polymer chain in a sea of monomer. And so there it's just readily available, just keep zipping up until you start running out of monomer. Once you start running out of monomer, then you have the same diffusion problem, but your polymerization has almost completed in a matter of minutes or an hour. In the case of the step growth, you typically have some other element than carbon and the backbone. You have some functional group, amines, alcohols, oxygens, ethers, some functional, organic functional group is in the backbone. So in a step growth, you might always look, is there something other than carbon in this backbone? It's more likely than not going to be a step growth polymer. If you look at the polymer and the entire backbone is carbon, 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 carbon bonds, that's probably a chain growth polymer. Okay, so you can almost just look at those two things and kind of define which is which is again why which is why polyurethanes fit under the step growth, because they do have something other than carbon in them. And in the case of step growth, we usually lose a molecule or we change the functionality, which means the monomer and polymer have different compositions. We can't call them the same thing. In the case of chain growth, the only thing we lose is typically a double bond, but all of the same elements are present in the monomer as in the polymer. We do not lose a small molecule, okay? And the last thing is step growth can be slow. They can take 24 or 48 hours. In the case of chain growth, they can be done in less than 5 minutes sometimes to get million molecular weight in less than 5 minutes. Questions on the compare and contrast those two different polymer types?
Yeah, I had a question.
Okay.
So could you explain why the polymerization rate on the chain growth is not affected by the monomer depletion? Because if the reagent's being consumed, wouldn't that affect the rate of the reaction?
It does only at the end when you have very little monomer left. Okay, imagine that your monomer is almost the solvent, and so there's no change in rate as your polymer chain is growing until it's like right at the end. So it's already at 1 million molecular weight or 2 million molecular weight. Now you're starting to have very few monomers around at that point. So your chain is almost as big as it can be, and there's only those last 5% of monomers that it's going to react. So this first, 1 million molecular weight is all running at the same rate until it has just a few monomers. Then it has diffusion control. Then you have to wait for those monomers to find the end group. So that's why it says it initially increases because of the availability of monomer until the end when you run out of monomers. Then you have to wait for diffusion. Does that answer your question?
Yes. So then with step growth, it's just decreasing the whole time.
Right, because if you think about it, small molecule diffuses faster than a bigger molecule, right? So if this molecule is twice as big as this is going to diffuse half as fast. So now let's hook those together. Now it's 3 times what it used to be. Now it's going to diffuse slower. Now 4 times slower, 5 times slower, 6 times slower. Now let's say you have 10 things that are 10 long. Well, now you have to have 2 10-thing longs have to diffuse to find each other to finally react. So see how it's going to slow down every single time you add something? The rate's going to continue to slow down. Does that make sense?
Yeah, that does.
Okay, great. Good question. Okay, let's see. Oh, only 20 minutes left. Okay, I got a few more slides here. Okay, so the general concept in step growth is we typically have 2 different functional groups. Now they can be on the same monomer, or they can be on 2 different monomers, but you typically have 2 different functional groups. And those 2 different functional groups will react with each other such to form the new backbone. So in the case of this right here, if they're both on the same molecule, so let's say we have right here, this is a carboxylic acid ester. So this is a benzoic acid derivative, and we have an ester here, we have an OH. So if you just set that monomer down and did nothing to it, nothing's going to happen, right? It's not going to react. But if you were to take this and add a catalyst or heat it up, add a little acid and heat it up such that it would lose the methyl group on the end here, then what you'll see is the hydroxide on the benzene ring, the phenolic OH is going to react with the ester and do a transesterification to give you your new backbone. Notice that backbone is oxygen, benzene ring, carbonyl. That OCH3 is no longer in that molecule, so it's lost a molecule, and I condensed away a small molecule. So it's changed from the monomer to the polymer. Now that's a really good way to do that because you don't have to worry about stoichiometry, because as long as this is pure, you have as many OHs as you have of the esters. Okay, but let's say you want to do something like make polyethylene terephthalate. Well, in that case right there, you would actually have two difunctional monomers. So you'd have one monomer that has two of the same functional group, another monomer that has two of the same functional group. And when they react, we still have that same reaction. In this case here, we're going to have the phenolic OH come and react with the carbonyl and kick out a small molecule, in this case, ethylene. I'm sorry, methanol. And then the other side is going to react and do the same thing. So this is more common right here, and we call those an AABB system. But notice the functional group that we create is the same on both sides. Okay, so in this case, we're making esters on both sides, and those esters are part of the backbone. Okay, in this case here, we're making only one ester as part of the backbone, but we're making two esters as part of the backbone. Okay. So in the case of why the reaction kind of goes slow, well, if we look at none of these monomers have reacted with each other. So none of these, in this case, we have a difunctional monomer here that A is going to react with B to form a bond. So we have, this is a monomer, 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 monomer. All these are monomers, okay? And then we react one monomer with one monomer to create a new functional group here. And we do that with a few of them. Well, only if 50% of the monomers have reacted with 50% of the monomers that are available, okay? So that means our degree of polymerization is actually 1.3, because only 1/3 of the monomers are actually in a state other than the monomer state. Now, if we react them again one more time to get a slightly higher, 75% of the units have reacted. We still have a very low degree of polymerization, only 1.7 repeat units on average, because we still have some that are monomers, some that are dimers, and some that are trimers, okay? So then if we get 100% reacted, in this case here, all of them have reacted, but there's still a dimer, a trimer, and a tetramer. We can have 100% reacted, but only have a DP of 3. The average repeat unit is only 3 long. We have 2 here, 3 here, 3 here, and 4 here. The average repeat is only 3, okay? So you can have 100% of your monomer reacted in a step growth polymerization, but still not have a high molecular weight polymer. You now need to wait for these larger fragments to diffuse to each other and react to make the higher polymer in the system. So that's why monomer depletion is so fast in step reactions, even though you're not making high polymer. Okay, so there's an equation associated with that, and we call this the Carruthers equation. And so the extent of polymerization, which is the fraction of the groups at any one time that are considered consumed, go into that degree of polymerization. If we look at this reaction, this equation right here at the bottom end, 1/1 minus P. So 1 is assuming unity, so everything's reactive. So if you have 1/1, meaning P is all of 100% of those units have reacted, it's going to be 1 minus 1. So you can't have that because that would be dividing by 0. So you're never going to have 100% of them react. So that when we have here, this difference, this ratio here is going to give you, so let's say you have 100 units here that have reacted minus the 1 divided by 1, that gives you a number that is going to be a whole number, and it's going to be higher than 1, is going to give you our degree of polymerization. Okay, so why do we say that P, that extent of reaction? Well, we are comparing the number of molecules, monomers, polymers, and oligomers from the beginning, typically the number of molecules of monomer that we start with, and then the number of molecules we have at some point in reaction time. So think about it. If we start with monomers here and at 0, and we stop it at some time X or T here, okay? In theory, with step growth polymers, we have no more monomer at time T because we consumed all our monomer early on in the reaction, right? So that our number of monomers that we started with is always going to be higher than the number of molecules we have at some time T, because we've added them together to get to that number. So if we look at our number of at the beginning is going to be greater than our number at the end, we get this ratio of 1 over 1 minus P. And that gives us our degree of polymerization. Question on that? So if you think about it, this number should always be greater than that number, because the number of molecules gets smaller and smaller because we're getting the size of the molecule is getting bigger and bigger. Okay, so we can actually play with this. I actually do this in my one of my research projects, is that I can't make my polymer over a DP of 20 because it will gel and it will completely not redissolve. So I actually have to use a degree of polymerization here of 20, which means I have a ratio of 100 to 95 for my monomers to make sure that my polymerization doesn't go too high, does not get too high a molecular weight. If I just change that to from 95% of one monomer to one monomer to 98% of one monomer to one monomer, that would give me a DP of 50, and that would gel out. Okay, so that works in that system. But in the case of other systems, by only having 95 to 100 right here, you're going to get a DP of 20, and that might be a powder. That might not have any good polymer properties. But by just upping it by this 3% to give it to 98, it might have sort of some properties. It might start to look like a polymer. But then if you get closer to 99.5 to 100, we now have a DP of 200. So that means we have 200 repeats in our unit here. And that could be a high polymer. So now if you wanted something that's a million molecular weight, you have to have 0.999 to 1 to get your DP to be 10,000 or 100,000. So look at that. You have to look at the purity required to get to this. So 99,999 out of over 100,000 functional groups must be reacted as designed or expected to get to a DP of 100,000. And then of course you can multiply the molecular weight by the DP, and that actually the molecular weight of the repeat unit by the DP, and that gives you the molecular weight of the polymer itself. Okay. Now, because of this purity requirement of 99.9999% of these reacting, only typically polyadditions have these high conversion rates. And that's everything from having just a minuscule amount of a defect in one of the systems, or any side reaction or any impurity will keep that DP from being high. So you need that exact perfect stoichiometric balance for that high DP, that high degree of polymerization. All right, so in chain growth, we actually have some opportunities for us to make that high polymerization. And part of that comes from the fact that it has to react a certain way. One of the most common ways is by the radical polymerization or an anionic or cationic. So it can be either anion. And in the case of that, we have to start the polymerization. And so that's initiation step. So we're starting with a neutral molecule that has no immediate addition polymerization propensity, right? So there's no reason for these to do any addition. They're stable molecules. So in the case of polyethylene, we would actually create a radical. And so that creates a radical at the end of the polymer chain. That radical is going to then go to the propagation step. In the case of something like polyethylene, in the case of the epoxy, to make polyethylene oxide, we actually use an anion to generate our nucleophile now, this oxygen then can react with another monomer here. So this is the growing functional group, and it only reacts at the end of the growing chain. Okay, so only those things that are initiated can be used in the propagation step. Now, in the propagation step we have here, in the case of the radical, it reacts with this double bond to create a new sigma bond, but it also creates another radical. Every time it reacts, it creates another radical at the end of the growing chain. Okay, so that's why the polymer weight is increasing, because every time it reacts, it creates a new radical that reacts with the monomer, that creates a new radical, reacts with the monomer. If your impurity can't react with a radical, it does not inhibit polymerization. In the case of the polyethylene oxide here, it keeps growing and growing and growing. And again, we have this oxygen anion at the end of the chain. If your impurity cannot react with an oxygen anion, it does not affect the polymerization. So the purity does not have to be there if it's not reacted to the system. Now, in the case of this, once you've consumed all your monomer, you can terminate this by either a radical-radical coupling. So two long chains grow into each other and there's no more monomers, so they just react with each other. And that creates no more radicals, the chain stops growing. In the case of an anion, you typically add something like water to it, an anion or a cation, you add water at the end, and that stops the reaction and gives you your termination step. All right, so that being said, and I got a couple minutes left, let's look at chain reaction as a function of dP. Okay, so when none of the molecules are reacted, they are all just sitting there, nothing happening right here. And if we initiate this and start growing, remember, it starts growing at the end of that chain. So only the one that's growing is consuming monomer. So that means at 50%, we're at 1.7 already. Remember, we were only at 1.3 before in the step growth. We're at 1.7 there. But at 75%, we now have a dP of 3. We have our repeat unit is much, much higher versus the number of molecules that aren't reacted, and therefore our dP is 3. And if we react all of them, because remember, it's growing at the end here, that's the only way it can react. By the time we have 100% reacted, we have a dP of 12, which is 4 times higher than that of the step growth polymerization. Okay, so does that give you an idea of why step growth and chain growth have different dPs at different points in the reaction? Okay, so let's see, I think this is actually kind of long. Okay, I'll start with this and we'll continue on this on Thursday, but I'll do polymer. Oops. Actually, let's start polymer nomenclature next time. Well, I'll let you go off for this one. Again, we're going to meet on this channel. This Zoom link on Thursday at the same time. Hopefully we'll be able to get through this lecture and I'll start the Nanocomposites lecture then. And hopefully in a couple of weeks, we'll be meeting live in Chem 133 over here on this side of campus. All right, any questions or comments before we head out today? I'll take that as a no. I'll go ahead and stop.